Welcome, Dr. M here. We're going to talk about hydroboration addition reaction across the alkenes. This reaction leads to formation of alcohols, but it goes through anti-Markovnikov rule, where we're surely not going to go through formation of carbocations, and we are not going to follow Markovnikov rule. But just to give you an idea of what's happening here, I just want you to picture this. The BH3, the borohydride added here, can be written as BH2 and a H. The BH2 is bigger than the H, so the BH2 should be added to the carbon that's least crowded, the carbon that's least substituted, and the H is added onto the carbon, sp2 carbon of the alkene that's most substituted. So this will go here in this case, and this will go here because this has only one carbon attached to it, and this has 3 carbons attached to it, causing some sterics. So you don't expect the BH2 to go there. This side is crowded than this side of the alkene. So it's going to be a Syn addition. It's gonna be a Syn addition. Okay, so it's a Syn addition, which means you're adding from the same phase. Syn addition is adding from the same phase, same side. You're adding from the same side. So the BH2 and the H are added from the same side. That's how you get your regiochemistry and just stereochemistry. So in this case, we are going to add the BH2 right here on the carbon that's least substituted, which is here, and you're going to lose the double bond. I'm just giving you a shortcut here. And since you're adding from the same side, the hydrogen should have the same dashed bond, assuming you're adding from the bottom. If you're adding BH2 and H from the top side of the alkene, then BH2 will go there and the H will go here. These two guys are the intermediates, which when oxidized, this is the oxidation step, because this is the hydroboration step. You're adding a hydrogen, the borane, which when you oxidize these intermediates, you're gonna replace the BH2s with OH. That means you're forming an alcohol, keeping the stereochemistry. So OH will be there, and the H will go there, it's still there, and then in this case, OH will be here, it replaces the BH2, and the H will be right there. Okay, so you get, starting this molecule, you're gonna end up with the 2 enantiomers. Again, for this reaction, you're adding a H and OH across the double bond, just like we've done here. Going anti-Markovnikov, because again, the hugest clue, you have a peroxide. Each time you see a peroxide in a reaction, expect anti-Markovnikov if you're looking at adding groups across the double bond. So the H should end up on the carbon that's more substituted, which is this, which means a carbon that has more carbons attached to it, and the BH2 will end up here, which in turn, in the second step, the BH2 is replaced to make an OH right here. So the OH should end up here, the hydrogen should end up here, with the OH having a wedge and the OH having a dash. How do you judge that? According to this reaction, if you're gonna put this metal away, that means something pushed it away, and it has to be the hydrogen that comes from the medium, because you're adding H and OH here, and here the hydrogen must have been added from the bottom phase. Now, because it's Syn addition, the OH should have same wedge bond as the hydrogen, and the OH must have the dashed bond or the hash bond as the hydrogen that was added. Because it's Syn addition, these bonds must be added from the same side, the same type of bonding in 3D, same type bonding in 3D. Okay, so you get enantiomers. Okay, again, for this example, next example, this carbon right there is the most substituted. This one has a hydrogen, at least has one hydrogen. This has none. This is least. This is the least substituted of the two. So the OH should end up here, the hydrogen should end up there. You're adding from the same phase, not going through a carbocation intermediate, no shifts. Syn addition. So the hydrogen comes here, and that means the OH should have the same bond, and it should be right there because it's Syn addition. Here we need the hydrogen to have opposites, which compared to the ethyl, so the hydrogen will be there here and the OH will be there. Syn addition, anti-Markovnikov, no shifts, no carbocation intermediate. Again, identify the most substituted carbon. So this is the most substituted carbon. The H should end up there, and this is the least. So the OH should end up there after the two steps. So we're going to put the H away, and that means the OH should be away. We are adding H and OH, anti-Markovnikov, not going through carbocation intermediate, no shifts, no rearrangements. So since this is dashed, the product will be, remember these products I just pre-drew them to save time, but you should expect if it's adding from the bottom, then the ethyl should be pushed up. If it's adding from the top, this ethyl should be pushed down, and that means your H should have a wedge here and your OH should have a wedge there, because there is Syn addition, same phase addition, pushing the ethyl away, if you're adding from the bottom phase, if you're adding from the top phase. This bold wedge just means you're adding from the top. Again, I've pre-drawn an incomplete structure of answers here, but let's start with adding from the top phase. On both sides, you're assuming an excess of reagent here. So if you're adding from the top phase, of course these two carbons are the most substituted, so the hydrogen should end up there because the hydrogen is small size, can easily access that area, and the OH should end up on the least substituted, according to anti-Markovnikov rule of hydroboration. So let's start by adding our H and OH using this cocktail reagent. On both sides, let's assume both alkenes are being attacked from the bottom phase. Let's assume both alkenes here are attacked from the bottom phase. That means the methyls will be pushed up, like in the first illustration, will be pushed up. Go ahead and add your hydrogen, the most substituted carbon, losing the double bond. So that's one option. Now if the additions, the mechanism is happening adding from the top side, the H and OH adding from the top side in an anti-Markovnikov fashion, no shifts, no rearrangements for this type of reaction, for hydroboration reaction, then you should end up with these two products where the H here should be added on the top. The H is added from the top. At the same time, the OH will be eventually added from the top. The OH ends up on the top. What's the relationship between these two guys? These are diastereomers because you're keeping this stereochemistry constant. So those two are diastereomers. Now, if it happens so that you're adding this side from the bottom phase to get these groups like that, H and OH like that, and this side you're adding it from the top phase, you will get this molecule. And here we are adding opposite of this, so we are adding from the top phase to your left. Regiochemistry, H ends up where there's more substituted, there's a more substituted carbon of the sp2 carbon on the alkene, and here we are adding from the bottom face. So those are the 4 possible products. Okay, practice. Now, what if the reaction needs you to show intermediate on the Haworth projection? This kind of drawings, Haworth. We know that once the reaction happens, you're adding H and BH2 from the first step. Here we will not combine the steps, you're doing them stepwise. And I started by telling you, think of it as H and BH2 to get the intermediate. The BH2 should end up on the most substituted carbon. The BH2 should end up on the least substituted carbon, which is this carbon of sp2 of the double bond, and the hydrogen of BH3 should end up on the most saturated carbon, which is here. And you are doing Syn addition, so the first molecule, assume we are adding from the top, then my H should be here, my methyl should be there, which is just this method. And that means since it's same phase addition, then the BH2 should be here. So that illustrates the addition we're talking about. You know, you have CH3 and H, those ones should end up on the same side. We are adding from the top, so they'll be flashed to the bottom. They'll be pushed back, they'll give way and be pushed back. So that's the intermediate for that. The intermediate for this, the other option that you get is if you're adding BH2 and H from the bottom, flashing the H and CH3 to the top. So BH2 here, the bottom, flashing H up, and H here, flashing CH3 up. So that's the hydroboration step. Giving you the intermediates. Of course, they are enantiomers. And if you do the oxidation step, you're simply replacing the BH2s with OH. So you just copy out what you have. Only the BH2 is changing. And that will be a final product on the Haworth projection way of drawing molecules, cyclic molecules. Okay, that's it for today. We've just talked about hydroboration. Okay, now what's the mechanism of addition? So looking at this example, starting with this alkene, which you should see is not same as that. This is a different starting material. As I said, H is going to be added on the carbon that's more saturated because H is small in size, no much hindrance experience, and BH2 will be added to the carbon that's least saturated, which is this side. So you end up with this product. So BH2 goes here, H goes there. You end up with this product, but you still have more hydrogens to do the same process like you did here. So you come with the second molecule of the starting material, still add hydrogen, the brown hydrogen, to the carbon that's more saturated, and the other group contain the carbon structure because now it's even bigger than the BH2 is going to be added on the side that's least substituted with, that's least crowded. You end up with this structure. You still have one more hydrogen to give from the BH3. This time we are giving off the hydrogen, this hydrogen right here. So do the same addition with the third molecule of the starting material. The hydrogen goes where the carbon is least saturated. The dialkyl borane will be added to the most saturated. The hydrogen goes to the most saturated carbon of sp2, carbon of the third molecule, and the dialkyl borane will be added to the side that is least saturated, least crowded. You end up with trialkyl borane. Now at this point you've already done your hydroboration, it's complete. Now the next thing you have to do is oxidation. The peroxide molecule will simply attack the borane. You know, the boron has an empty p orbital. You end up with this salt, and then we're going to have a migration of one of the groups. I'm choosing to migrate this top alkyl group. You're going to get that. and the OH is going to fall off, so you get this structure. Then repeat this process twice to do 2 migrations. You're going to put you're going to end up with 3 oxygens around the boron with 3 alkyl groups. Now at that point, remember you're adding sodium hydroxide here. Sodium hydroxide will use the hydroxide to attack the boron center. You end up with this molecule, and then from this molecule we're going to lose 2 groups. It's going to break apart to get these 2 structures circled in green. And how does that happen? This bond just breaks towards the oxygen on one of the ethers. That's how you're getting these structures a leaving group, and you'll be left with this structure, which is just the rest of the molecule down here. Okay, now come with this structure, continue the process. We're going to repeat this step twice by attacking the boron, so that this group leaves. If you repeat twice, you're going to get these 2 molecules. Repeat this step twice, going to get these two molecules, and end up with 3 alcohols at the end. So this is one of the most complex mechanisms you'll get in organic chemistry, but just practice, you should get it. But personally, I usually don't test on mechanism on this reaction, but it's good to just know what's going on.